Hello, welcome to College Algebra, section 12.5, partial fraction decomposition. My name is Rob Reynolds. Today we're going to learn how to, instead of adding fractions, we're going to try to pull them apart and decompose them. This is a useful skill when you get to calculus. So just reminding you to choose a common denominator when you're adding fractions. You choose every factor as many times as it appears in each denominator. We're going to learn how to go backwards here in a moment. But let me refresh your memory how to go forward. So this factor is missing the x plus 2. So if I multiply the bottom by x plus 2 and the top by x plus 2, I can bring over a 2x plus 4. This denominator is missing the x minus 3, and I would actually call this a negative 1 that you distribute. So negative x plus 3, giving you combining like terms. 2x take away x gives me x plus 7. So what we're going to do in this video is move backwards. So if I give you x plus 7, we're going to decompose it into two separate fractions. So to do that, the first thing we do is factor. Factors of 6 that differ by 1 are 2 and 3. Signs are going to be different. The larger term is negative, forcing this to be positive. And then I, again, choose every factor as many times as it appears in each denominator. And I'm going to say plus, although the value of b might be negative, and then that would force this to be a subtraction. But I know that it's got to be equal to x plus 7 over x plus 2 and x minus 3. So what I'm going to try to do here is multiply both sides by the common denominator, which is x plus 2, x minus 3. Multiply over here, x plus 2, x minus 3, and then distribute that to every term. It looks like I've multiplied the left side twice and the right side once, but I didn't. I just multiplied both sides by the red and then distributed every term. And then I'm going to cancel, leaving me with a times the quantity x minus 3 plus b times the quantity x plus 2. All of this cancels. X plus 7. So if I do a quick let statement here, if we let x equal 3, which is really convenient because if you let x be 3, then that drops out the a term, I'm left with 5x's equals 3 plus 7, 10, and x will equal 2. I'm going to do another let statement. Let's let x equal, well, to wipe out the b term, I'll go for negative 2. So I get negative 5a is equal to negative 2 plus 7, which is 5, and a is negative 1. And then I can go back and write this fraction, negative 1 over x plus 2 over x minus 3. And of course I could flip that, swap that around, and I believe that's what we had started this video with. So let's review some of the rules that we're going to use. Here's how the author worked it out. Some of the rules are this. I'm going to choose every factor as many times as it appears. So I need an x, and I need an x minus 4, and that means I'm just going to choose an a and a b term. So number 1 looks like I would match it with letter b. I'm choosing each factor, and I just choose an a and a b up top. Number 2, this is an x is a factor and an x squared is a factor of this first x squared term. So not only do I need x, I also need an x squared and I need an x minus 4. And that looks like c. Notice I'm just using a, b, and c, even though this is not linear. That's a quadratic, but it's the product of linear factors. And that's really the most important thing. Look for products of linear factors. And that yellow x squared is the product of linear factors because it's x times x. Both of those are linear factors. Now, this is not the product of a linear factor. There's no way to factor x squared plus 4. You can try, but you'll be wrong. So I'm just going to look for an x for one denominator. I'm going to look for this for the other denominator. But since this is not the product of a linear factor, I put a linear function up top. Instead of y equals mx plus b, this is bx plus c, but there's my constant because this is to the first. But if I can't factor this and it's not the product of linear factors, then I put bx plus c up top. Now, number 4, it's x, and then this does factor to x plus 2 and x minus 2. So I just need a, b, and c because these are all products of linear factors, and that would go with answer A. So don't solve just looking at products of linear factors. I would factor this, x minus 14, and then I would stick an a and a b because both of those are products of linear factors. Here it looks like I can factor factors of 3 that add up to 4, a 3 and 1. Again, I would just choose A and B because I can factor those. So there's the first answer. There's the second problem answer. This one, I think I can factor out an x squared, leaving me with 4x plus 11. Now remember, this is really x is a factor of x squared. So I'm going to choose an x, I'm going to choose an x squared, and I'm going to choose a 4x plus 11. And since those are all products of linear factors, I choose A, B, and C, just like the author did. This one I'm going to have to choose x plus 2, that's a factor, x plus 2 squared, that's a factor, x plus 2 cubed, that's a factor, and x plus 2 to the 4th, that's still a factor, and these are all products of linear factors, so I would choose A, B, C, and D. This one I think I can pull out a 2x, leaving me with x squared plus 4. Aha! This is your first example, not the product of linear factors, but 2x is, so I would choose a 2x, and I would choose an x squared plus 4. Here's an A, because this is just linear, but this is not linear, so I'd put a linear up top, bx plus c. And again, I'm just setting up. I haven't really shown you how to get in to solve these, but I just want to make sure that you can set these up correctly. So here, x and x squared are both factors of x squared. And then, oh my gosh, let's see, 3x minus 1, and then a 3x minus 1 quantity squared. Products of linear factors, product of linear factors, product of linear factors, product of linear factors, so I would go A, B, C, D. Alright, enough practice. Oh, I've omitted this from but if you ever see that the degree of the numerator is greater than the degree of the denominator, you're going to have to do long division first. Hopefully I've taken out all of these problems. This will not appear on your test or your final, but you would simply divide and get it down to a proper fraction. This is called an improper fraction. But x cubed goes into x to the 4th x amount of times, and then you start distributing and do some long division. Then you'd ended up with some fraction that you would try to decompose at the end. So working a problem out from its entirety, because all we were doing is setting up, I would first step try to factor. This is going to give me x and x squared plus 4. This is an a, this is a bx plus c term. I'd multiply everything through by the common denominator, which in this case is x squared plus 4. I'd write it on every term, x squared plus 4. Again, it looks like I multiplied the right side twice and the left side only once, but I didn't. I just multiplied both sides by red and then distributed to every term. Everything cancels over here, giving me 3x squared plus 4x plus 4. The only thing that cancels on this side is the x's, so a times x squared plus 4, and all of this cancels, leaving me with bx plus c times an x. So my let strategy that I was using before doesn't work real well with this because it doesn't drop out the a or the b term. So I'm going to show you a one-to-one process that works too. If I just continue multiplying this out, I get ax squared plus let's go call it 4a, plus bx squared plus cx. So I'm going to reorganize this. This is just a constant, which I can see matches up with the 4. So all of a sudden I know 4a has got to equal 4, because that's the only constant in here, and I know constants have to equal constants. So I would say a has to equal 1. Another matchup would be, let's see, my x squared terms has to equal 3x squared. So I'll write that out. I know 3x squared has to equal, in fact, I'll even factor this. Let's pull out an x squared, and let's leave it with a plus b. So since x squared equals x squared, I know 3 has to equal a plus b. But we've already solved for a as 1. So I would say 3 is equal to 1 plus b, or b equals 2. That leaves me with my last term. I know 4x has to equal cx. So again, I'm just doing a one-to-one. I know my x squareds equal x squareds. I know my x's have to equal my x's. Therefore, c has to equal 4. Now I've got the value of a, b, and c, and finally you can write the equation. If you'd like to go through and solve this through matrices, you can. You can see how they're starting to write some systems of equations. You could dump this into a matrix and do RREF. Watch some of my previous videos to look at that. But here's that final answer. Feel free to pause the video and look at what the author did here. Someone once told me, a student once told me, if you only see A's and B's, try some let statements. But if you see A, B, and C, try to write equations and do that RREF. I don't know if that's proven or if that's true, but that's what one student told me that they always do. I haven't looked into that long enough to figure out if that's actually true or not. I would set this equal to x squared plus 2 and then x squared plus 2 quantity squared. This is not the product of the linear factors, so this is ax plus b. This would be cx plus d. Ugh. Then I'm going to multiply both sides by the common denominator. Hopefully a lot will cancel. Let's see. All this is gone, so I'm left with 8x cubed plus 13x. Only one of these cancels with one of those, so I'm still left with ax plus b times one of those, x squared plus 2's. And I think all of this cancels, so I'm left with plus cx plus d. I don't see any clever let statements again, so I think I'm going to multiply it out and try my 1-to-1. Actually, I have to FOIL this out. Oh, jeez. Ax cubed for the first term plus 2ax plus bx squared plus 2b plus cx plus d is equal to 8x cubed plus 13x. Actually, let's write this so you can see it a little bit clearer. This is actually 8x cubed plus no x squareds plus 13x plus nothing. So now I'm going to stick my x cubes with my x cubes. If you want to write equations, you can, but I think I can just solve this. 8x cubed equals ax cubed, so a equals 8. My x squared terms, 0 is equal to b. So it looks like b has got to equal 0. Let's see if we can put the 13 with the x terms. I'll try to factor out an x from this blue, leaving me with 2a plus c equals 13x. So I know 13 has to equal 2a plus c, and I've already got the value of a, so 13 equals 16 plus c, so c better equal 3. And looks like I have a constant left over. 2b plus d equals 0. So I'll write that. 2b plus d equals 0. I know b is 0, so d has to equal 0 as well. Let's see if the author got the same thing. Yeah. So here's the final solution. Did I have another 0? Yeah, b was 0 and d was 0. So if b and d are 0, the only thing I have left is 8 and the 3. It looks like the author agrees. There's the 8x and, oh, is that a negative 3? Did I get a negative 3? Yep. Oop, I didn't, but I should have. All right, very, very good. So that's partial fraction decomposition. There's lots of problems from the book you can try. Again, feel free to write equations. If you want to pause these videos. Oh, this is kind of interesting. Instead of writing the positive, you could leave it in factor form. They might leave it 2x minus 8. I worked out a couple problems here. If you want to work this out and then pause the video and see if you can get this, that's fine. Your answers might, again, look a little different. So instead of saying minus x minus 1, you could distribute that negative throughout. Number 36, I worked with my class. There's the solution. and 38. Go ahead, pause the video here, see if you can work it out, and there's worked out solutions for you. All right, so if you have questions, feel free to email me.